From the very first time we looked at the night sky, humanity has been captivated by the idea of traveling beyond our world, seeking a way to reach the farthest corners of the cosmos. But how could we overcome the vast distances that separate us from other stars, galaxies, and worlds? For centuries, this question has plagued physicists, explorers, and dreamers alike. Could there be a shortcut, a doorway through space itself, that defies the limits of distance and time? In the early 20th century, theoretical physicists like Albert Einstein reshaped our understanding of the universe. They showed us that space and time are not separate entities, but part of a single, unified fabric known as space-time. This theory opened the door to the possibility that space itself could be bent, twisted, and connected in ways previously unimaginable. One of the most intriguing consequences of these ideas is the concept of the wormhole, a theoretical bridge between distant points in space and time, also known as an Einstein-Rosen bridge. What is a wormhole? How does it work? And could these incredible structures be more than just a fascinating mathematical curiosity? Today, we'll explore the science behind Einstein-Rosen bridges, the potential they hold, and the incredible possibilities they might offer to future space explorers. To understand wormholes, imagine the universe as a sheet of paper. If you fold the paper, two distant points on the surface come together. Now, imagine drilling a tunnel through the fold. This is the essence of a wormhole, a tunnel-like structure that connects two separate points in space-time, creating a shortcut across the universe. In essence, a wormhole is a topological feature in the fabric of space-time, connecting different regions of space and time. Picture two distant galaxies, each light years apart. With a wormhole, you could theoretically traverse that distance almost instantaneously, bypassing the constraints of time and space. The concept of a wormhole emerged from Albert Einstein's general theory of relativity, which describes how mass and energy warp the fabric of space-time. According to this theory, gravity is not simply a force but the effect of this curvature. Objects follow the paths dictated by the warping of space-time around massive bodies, like stars and black holes. In 1935, Einstein and his colleague Nathan Rosen proposed a solution to his field equations, a mathematical description of a bridge between two black holes, creating a connection that could potentially link two distant parts of the universe. This theoretical structure would later be called an Einstein-Rosen bridge, or simply a wormhole. The Einstein-Rosen bridge is a solution to Einstein's field equations that connects two separate points in space-time through a kind of tunnel. In the original proposal, this bridge linked two black holes, regions of space where gravity is so intense that not even light can escape. However, this early conception of the wormhole presented an intriguing problem. The bridge was not stable. The passage was effectively a singularity, a point where the curvature of space-time becomes infinite and where the laws of physics break down. This meant that the bridge was not physically traversable. Any object that attempted to travel through it would be crushed by the immense forces of gravity at either end. So, while the Einstein-Rosen bridge exists mathematically, it didn't offer a viable way for astronauts to travel across the universe. The original wormhole was a non-traversable phenomenon, and the idea of using it for practical space travel was dismissed as a mathematical curiosity rather than a realistic pathway for interstellar journeys. The next step in the exploration of wormholes came when physicists began to wonder if it was possible to stabilize an Einstein-Rosen bridge and create a traversable wormhole, one that could allow for the passage of matter, like spaceships or even humans. For a wormhole to be traversable, it must be stable. This means that the gravitational forces within the wormhole cannot collapse the structure before something enters or exits. To solve this, theorists propose the existence of a substance with negative energy or negative mass, what is commonly referred to as exotic matter. Exotic matter is a form of energy that behaves in ways opposite to ordinary matter. While ordinary matter has positive energy and mass, exotic matter would have negative energy and mass. This negative energy could theoretically counteract the immense gravitational forces that would otherwise cause the wormhole to collapse. In 1988, physicists Kip Thorne and Mike Morris proposed that a wormhole could indeed be stabilized using exotic matter, creating a stable passage that could allow for safe travel. However, such exotic matter remains purely hypothetical and has not been observed in nature. Its existence would require an entirely new understanding of physics, especially quantum mechanics and the structure of space-time. Even if exotic matter were discovered, the challenges of wormhole travel would remain immense. One of the primary problems is the stability of a traversable wormhole over long distances. A wormhole large enough to accommodate a spaceship would likely contain extreme gravitational forces, tidal stresses, and other unpredictable phenomena. The creation of a wormhole also poses the question of energy. The amount of energy required to manipulate space-time on such a vast scale would be astronomical. Even with exotic matter, scientists are unsure whether we could generate the necessary energy to stabilize and maintain a wormhole, let alone travel through it. Another significant issue is the potential paradoxes wormholes could create. If a wormhole allows for faster-than-light travel, it could also allow for time travel. In theory, one might travel back in time, altering the course of events, leading to the creation of causal loops or paradoxes. For example, one might travel into the past and prevent the very creation of the wormhole, creating a logical inconsistency. This leads to the grandfather paradox, where actions in the past contradict the future. These paradoxes raise important questions about the nature of time and causality in the universe, and some physicists believe that a complete theory of quantum gravity, which merges quantum mechanics and general relativity, would be needed to address these issues. In recent years, the concept of wormholes has expanded beyond just connections between distant points in the same universe. Some theorists suggest that wormholes could be used to connect not just different locations in our universe, but also different universes entirely. The idea of the multiverse, the hypothesis that there could be an infinite number of parallel universes, each with its own laws of physics, suggests that wormholes could form connections between these universes. If true, wormholes could allow travel between alternate realities, opening up a vast array of possibilities. The many-worlds interpretation of quantum mechanics suggests that every quantum event could result in the creation of a new universe. If wormholes connect these universes, they could serve as bridges between multiple realities, enabling travel across dimensions. However, this idea remains speculative and has not yet been tested by empirical evidence. Wormholes have become a staple of science fiction, fueling stories of interstellar travel, time travel, and alternate realities. From the iconic Star Trek series to films like Interstellar, wormholes provide a dramatic way to explore the universe and its mysteries. These depictions often take liberties with the science, showing wormholes as convenient, instantaneous routes for space travelers. But despite the fictional embellishments, these portrayals are grounded in real scientific concepts. One of the most famous portrayals of wormholes came in Christopher Nolan's Interstellar, where the crew travels through a wormhole near Saturn to reach distant star systems. The movie worked closely with physicists, including Kip Thorne, to ensure that the science behind the wormhole was accurate, even though it remained a work of fiction. Wormholes also appear in novels like The Forever War by Joe Haldeman, where they are used to explain faster-than-light travel, and Contact by Carl Sagan, where a wormhole allows communication between Earth and an alien civilization. These works inspire our imaginations and invite us to consider the possibilities of what might lie beyond the farthest reaches of space. As we venture further into the depths of space and explore the mysteries of the universe, wormholes remain one of the most intriguing concepts in theoretical physics. Could they one day serve as shortcuts for intergalactic travel? Could they hold the key to connecting parallel universes or unlocking the secrets of time travel? For now, wormholes remain speculative, confined to the pages of textbooks and the realm of science fiction. But as our understanding of physics deepens, particularly in the fields of quantum mechanics and general relativity, we may one day find a way to unlock their secrets. The study of wormholes reminds us that the universe is full of mysteries, many of which are still waiting to be uncovered. As we continue to explore the far reaches of space and time, one thing is certain: the journey is just beginning, and the possibility of crossing the cosmic divide may not be as far out of reach as we once thought.